have been what happens is that as the course becomes as
Hmm.
we go deeper into the course, there are many
Okay.
students who will drop off generally. Uh,
Okay. That's
that's how it is. Students drop off, and the course becomes difficult for them. Whatever happens.
yeah,
But
yeah, yeah,
this is not uncommon. I have been TA before.
yeah, yeah.
This
Understand,
happens.
understand.
All right, let's
Okay,
start.
but I
Uh,
already start.
So last week we looked at condition numbers, and
Hmm.
one of the questions that we had asked last week was, uh, so we
But
were perturbing not the matrix, we were perturbing the. So if we were solving something like ax equals
AX. Hmm.
b, then we were perturbing this b. We were not perturbing this a. So,
Yeah, yeah.
and we saw that if we perturbed B, then the condition number that we were getting, this, that is the difference in the solution by X.
Yeah,
Uh, this came out to be equal to the condition number of A
yeah, yeah.
times del B by B. Right.
Yeah,
So
that's true.
today we will, yeah. So today we will see what happens when we perturb A.
Oh, are you started the recording or?
Yeah, I have started the recording.
Okay, okay, yeah, yeah. Because maybe
Yeah,
after maybe publishing, it is available for everyone. No? That's why. So then
yeah. The
maybe I
recording
will
is going
mute
on.
the call.
Yeah. So today we will study what happens when we put up A. Uh,
Sir, if you are maybe I will I am just if you want to if you really want to explain this, we will explain. Otherwise, we'll move to the today's session. Sir. Please explain about least square and regression analysis. Can you?
yeah. I will explain this. Then I'll move on to least squares. Okay.
Okay, sir. Yeah, yeah. Okay, sir. Yeah.
Yeah. Let's do this. This is important. This was not covered last week, and there was no
Okay, sir.
assignment question also based on this. So like that's why it was kind of got unnoticed. Okay. So
Okay,
what
sir.
happens when you perturb A? So let's say A gets perturbed to A plus some delta A. And now we want to solve A plus delta A times X is equal to B. Okay. So the question is, when is so the first requirement is that A plus delta A has to be uh, has to be invertible. Only then this thing makes sense. Otherwise, it doesn't even work. So first, what we will give is that we will give a sufficient condition, not a necessary condition, but we will give a sufficient condition. We will give a sufficient condition uh, for A plus delta A to be invertible. Okay. So let's state what is that sufficient condition. So lemma, if one second, if delta A by A is less than equal to 1 by the condition number of A, then A plus del A is invertible. Okay, let's look at a quick proof. Uh, this proof is different from what is there in the notes. I kind of found a more neater proof. So yeah, so you can rewrite this condition as follows. So this uh, so K2 of A is equal to norm of A times norm of A inverse. So we can rewrite this condition by saying that del A 2 is less than or equal to 1 by norm of A inverse. Now, uh, we may ask uh, 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 now uh, now we may ask the question, when can I guarantee that A plus del A is invertible? So that is equivalent to asking the question, uh, when does A plus del A times X not equal to 0 for all X? Okay, that's this is equivalent to saying that A plus del A is uh, is invertible. So that's equivalent to saying that AX is equal to minus del A times X. Okay. Uh, so so you can write in this way: if for all x, if for all x, uh, del A x norm, or yeah, del A x norm is smaller than is smaller than uh, A x, then then we are uh, guaranteed that uh, AX is never equal to minus del A of x, right? Okay. Now we can easily assume that x norm of x is equal to 1. It will not make any difference over here. If it's not equal to 1, you can just divide both sides by norm of x and arrive at the same conclusion. So, so if max of norm x equals to 1, del ax is less than min of del x equals to 1 ax, then uh, star is always satisfied, right? But this is just equivalent to saying that norm of del A is less than. So what is this quantity? This quantity is equal to the the min norm. So this is equal to AM. So if it was max, it would have been norm, but this is the min. So this is a valid quantity. This is because A is non-invertible, because A is invertible, sorry, because A is invertible. This is some quantity uh, which is bigger than 0. So this quantity is actually something bigger than 0. So, if we can guarantee this condition that the norm of del A is smaller than del A is smaller than the min of this quantity, then we are done. Now notice that uh, we proved this last class that this quantity min del x equals 1, ax, a, which is basically this quantity, is equal to 1 by norm of A inverse. Uh, we proved this quantity. We proved this. I mean, basically, that's how you get the. Uh, 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 just recall that k of A is equal to norm A times norm A inverse. That is equal to the norm of A by norm of A n. Okay. So essentially, what we are saying is, if del A norm is smaller than 1 by A inverse, then then uh, we are done. This is what we set out to do. So this is what we set out to do. So what we can say is that if this delay is smaller than this quantity, we're actually uh, yeah, we're actually done. So now the question is, uh, what is this quantity delay? So for um, so this delay has to be smaller than uh, the smallest singular value of A. Okay, or if you write it in terms of if I is completely diagonalizable and you have these eigenvalues of A, then delay has to be smaller than the smallest eigenvalue of A. Okay, for this condition to be satisfied. So by and large, if A is a well-conditioned matrix where the smallest eigenvalue is not too small, then you can safely guarantee that for small perturbations of A, delay by A, delay plus A is going to be invertible. And so it makes sense to study this problem. Uh, so now we will study uh, A plus del A times x plus delta x is equal to B. So B is kept constant. We are perturbing A, and that leads to a yeah. And so what we'll get is del A times x plus AX plus A delta x plus delta A times delta x is equal to B. Now AX is equal to B, so we can cancel them both sides. And what we get is as follows. Uh, yeah, there's also one approximation that we can take is that we can take this. So del A times del X is a second order term. I hope you understand what a second order term is. Whereas this term and this term are first order terms because they include, they're called first order terms because they have uh, uh, first order perturbations, whereas this is the product of two perturbations. So this is small in general. So you can ignore this quantity. And what we have is del A times x plus A delta x is equal to 0. Um, Okay, I guess I guess we should not ignore this delay upon del x. So let's keep this delay upon del x. Not an issue. We can write it in this way. We can write del a times x plus a plus delta a times delta x. Sorry, just I'm writing. Just give me one. Uh, okay, sorry. Yeah, so this x plus del x is the new solution. Uh, yeah, so a delta x is equal to minus delta a times x plus delta x, or delta x is equal to a inverse uh, delta a times x plus delta. Right. So now let's apply norms both sides. So we get del x norm is equal to uh, norm of A inverse times delta A times x plus delta x, uh, which is less than equal to A inverse norm times del A inverse norm times x plus delta x. Right, which is itself less than or equal to A inverse norm times del A inverse norm times x uh, plus delta x. Okay. Now, we can get the condition number from here. So let's just write it as K2 of A. Okay, let's just write K is times delta A upon A times x plus x. Okay. Uh, and so just bring these over here. So we get 1 minus K A times delta A by A times delta x is less than or equal to A A delta A upon A now times x. Okay. Um, right. So what this gives us is as follows. We get delta x by x norm is less than or equal to K A times 1 minus K A times delta A by A times delta A I now now there's one approximation that we make, which is that if A is well conditioned, uh, so if A is well conditioned, then basically K is uh, small, and Ka times del A is uh, a small quantity uh, of the second order. So basically, that approximation we are taking it over here, and so we can. So if A is well conditioned, we can assume that this one minus A times del A upon A norm is roughly equal to one. Okay. So then what we get is as follows: we get delta x by x is less than or equal to A times delta A by A. So if A is a well-conditioned matrix, the condition number of the problem where we are perturbing A and keeping B fixed uh, is also the condition number of A. Okay, which is very interesting. That in both cases you get the condition number to be equal to A. If you perturb B and keep A constant, then also it's the condition number. If you keep B constant and perturb A, then also you get the condition number, provided the matrix A is well conditioned. Okay. Uh, so yeah, this is what we need to keep in mind. I just want final result. I'm just going to state it. So Uh, what happens when both uh, when both A and B are perturbed? Uh, so the that sensitivity analysis is basically this: delta x by x is less than or equal to Ka times 1 by A uh, delta A by A. Okay. As before, you can assume this quantity to be small. Yeah, you can assume this quantity to be nearly equal to 1, so that the condition number is again equal to K basically. Okay. Right. Okay. Yeah, as you notice that finding uh, uh, these condition numbers are important. Uh, uh, I think as part of this course, the only condition number that you're required to find out is what happens when what happens to this problem X, basically the matrix vector multiplication problem. Uh, but there are lots of interesting problems if you want to look up some advanced examples of how condition number gets calculated. Then you can look at something like the QR decomposition. So in the QR decomposition, let's say you fix one method of getting the QR decomposition. It could be rotators, reflectors. It could be just the Gram-Schmidt orthogonalization process. And you get a matrix A, and you produce the Q and the R, and then of course you can study what happens to the Q and R if you slightly perturb A. Yeah, though those can lead to some uh, uh, somewhat complicated analysis. Uh, yeah, in general it's not an easy problem. So yeah, just to kind of conclude on this area, it's not at all easy to find condition numbers of problems. In fact, in numerical linear analysis, this is an active area of research. There are many problems for which computing the condition number of the problem, giving like sensitivity analysis of the problems are actually open problems. They're open for a very long time, and if someone can actually if someone can give the solution to those problems, uh, uh, then uh, that would be considered a very big achievement in this area. Okay. Uh, with that said, uh, let's now move on to the least square approximation, uh, and then some linear regression, uh, and then we'll look at the problems from this week. Okay. Yeah, just on a final note for this kinds of problems. So if your problem f, so let f be the problem that you're trying to solve, and it takes inputs, let's say x1, x2 up to say some xk. So an example would be like finding the solution of the system Ax equals to b. So then uh, uh, so then your input is a matrix A and B, and you want to produce a solution xsol. Uh, so you can think of it as a function where you have A, which is an invertible matrix, and some column vector B, and you produce the solution xol. So in general, your problem can have uh, uh, So the parameters of the problem can be like, let's say, denoted by some x1, x2 up to, let's say, some xk, where each of these xi's are basically some vector inputs. So in this case, when we talk about the, so let's say this is the problem that you are studying. Y is equal to f of some x1, x2 up to xk. Then the condition number is basically requiring you to compute this. You want to express del y by y norm uh, to be less than equal to the condition number of this problem kf. Uh, kf, and when there are multiple inputs, you will write it in this way: del x1 by x1 dot 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 up to del xk by xk. Yeah, so basically the smallest constant which permits this inequality for reasonably small perturbations of del x1 up to del xk is going to be the condition number of the problem. So this is how you generally express it. Uh, an example being over here where you have two inputs A and B and you express the conditioning of the problem like this. So that's how the condition number is defined for when there are multiple inputs to the problem that you are perturbing at the same time. Okay, and then if there are multiple outputs, again, this may not be needed, but you treat each output separately. So let's say f uh, x1 up to xk produces, let's say, some r output. So let's say y1 up to yr. You will treat each of these separately. So you will write del yj by uh, yj is less than or equal to some constant k times all these perturbations there. And the smallest k uh, uh, which allows for each of these outputs to be expressed like this is going to be the condition number for the whole k. So an example would be the QR decomposition, where you have a matrix A as an input and you're producing two outputs basically. The Q and R matrix are the two outputs, and in that case you express the sensitivity. You separately consider q as one output variable, and you consider r to be another output variable, and you express the conditioning of q separately, r separately, and you then combine them. That's basically how you do. Okay, I guess that would not be needed in the course any further. Okay, so now let's come to least squares. uh, so we looked at least squares last week, uh, where we uh, where we basically uh, where we basically saw how to get the least squares from how we basically saw how the least squares problem is effectively equivalent to finding a point in a hyperplane which is closest to the input vector basically. So essentially what you're given is you're given some uh, hyperplane A, uh, which is generally represented as a matrix, some A1 up to AK. So these A1 to AKs are the column vectors of the matrix, and they form a basis of this hyperplane. So when I say hyperplane, the hyperplane or hyperplanes always pass through zero. So they always contain the origin, unless I say otherwise. That in which case I'll call it an affine plane. I won't call it a hyperplane. But yeah, these are all hyperplanes, so they always pass to the origin, and they are spanned by A1 to AK. And there is some vector B given to you, and you want to compute uh, minimum of minimum over x, ax minus b uh, under the two norm. Okay, if you use the one norm, then or if you use the one norm, the soup norm, then what happens is that the problem is no longer smooth. And So the one norm and two norm, just by the nature of the norm, is that the norms are not smooth, uh, and so you cannot solve this minimization program by taking derivatives and setting them to zero. Okay. Now, for higher norms, like let's say in general, if you look at a P norm, uh, then the P norm does not come from an inner product. Okay. So let me just write it. The P norm in general for P greater than 2 does not come from an inner product. Okay, but the P norms etc. are all smooth norms. So you can of course take a derivative and set it to zero. So that is one way of getting it. But this geometric intuition that you find a point B or you find a point, let's say B hat, which is such that B minus B hat uh, is orthogonal to A, this hyperplane A. Uh, uh, this geometric intuition cannot be used unless the norm that you're dealing with comes from an inner product. So the two norm comes from an inner product, and so this geometric intuition is correct over here. Okay. Um, so yeah, so in general, given least squares problem, you can either with the two norm, you can either take derivatives and solve it, or you can project this point B onto this hyperplane, uh, and then you take the derivative. So for that, what you need to do is you take A. So notice that I'm writing this matrix as A, and I'm also representing this hyperplane by A. It's an abuse of notation. So I'm not, just so that the amount of symbols I use is kept in check. I'm going to use the same notation. A also denotes the matrix, or A also denotes the hyperplane. So equivalently, what you can do is you can find a representation and an ortho normal basis for A. So you can find some orthonormal basis Q1 to Qk, uh, such that these guys span A, and Qi Qj is del ij, and norm of Qi is del I. So you find an orthonormal basis of A, and then you can write this B hat as equal to basically uh, you can write it as sum over of inner product of B with Qi times Qi, uh, which uh, which is just equal to uh, if you arrange these vectors as columns, that is equal to Q times Q transpose B. So that is your B hat, and you are essentially interested in computing the distance between B minus B. Essentially, the distance between B and B hat. Okay. Uh, Alternatively, there is a closed form expression for this, and the closed form expression is basically equal to this. Let me just write it. Uh, the x, so basically arg min of x, uh, ax minus b norm is equal to uh, a transpose a inverse a transpose b. Uh, so essentially, the x which solves for this minimization program is equal to A transpose A inverse A transpose B. And this is known as the pseudo inverse. It's denoted by this number. Okay. So yeah, whatever is convenient to you, you can use that to solve this. Now, let's see how the least squares helps in what we call a regression problem. So now we come to regression. So what we basically do in a regression problem. So the idea of a regression function of a regression problem is to uh, approximate an unknown function uh, with uh, with a set of known basis functions. So what we have over here is, let's say we have a map F from some vector space Rn to R. So it's a function uh, which takes vector inputs, which takes some x written in coordinates as, let's say, some x1 to xn, and sends it to some real number points. Okay, and this function is unknown. So you do not know the analytical nature of this function. What you know, however, is you know the value of the function at certain points. So we know the value of f at certain points. Okay, so these set of points are sometimes known as the training set. Okay, so there exists a couple of points. I'm going to write it as some x1, uh, x1 up to, let's say, some xn. So I'm using a superscript notation to distinguish from the subscript notation, which I'm going to reserve for coordinates. So each of these x1s to xn are actually vectors. Okay, and we know, and so this is given to us, and what is also given to us is this. So we have a couple of points. So there are n many points, and we know the value of the function at those many points, but we do not know the analytical nature of the function. And what we want to approximate this function using a set of what we call basis functions. So what you do is uh, choose some, yeah. So we know the basis functions. So uh, let phi 1 up to phi r be the basis functions. Okay. And in a typical linear regression problem, what we do is uh, uh, we want to learn a set of parameters. So let me write it. We want to learn uh, parameters alpha 1 to alpha r. So each of these alpha i's are scalars. They are not vectors. Okay. Such that if I denote a function f hat, uh, which is itself dependent on these parameters alpha 1 to alpha r, and I denote this function as alpha 1 phi 1 plus up to alpha r phi r, then uh, f hat alpha 1 to alpha r uh, approximates, in quotation, approximates, yes, okay, uh, So we want to learn these parameters alpha 1 to alpha r such that a function represented as a linear combination of these basis functions approximates f. So uh, uh, what do we mean by approximates f? So it depends upon the choice of an error function. So uh, error function. So basically, let e be an error function. So an error function uh, is a map from R to R greater than equal to 0. So it takes non-negative values, and what we want is we want to minimize um, sum over of j equals to 1 to n uh, f x sorry uh, error of f f x j minus f of f hat alpha 1 to alpha r acting on xj. Yeah, we want to minimize this, uh, and we want to choose parameters such that this is minimized. Okay, so essentially, this is the structure of a linear regression model, linear regression problem. We have with us a function f, which is known to us at a certain number of points. We choose a set of basis functions that depends on the problem. Different kinds of problems may require you to choose different sets of basis functions, and what are good basis functions for f, that is an entire area of study in itself. But you are given to you the basis functions, so you know the basis functions, you know the analytical nature of the basis functions. But what you want to do is you want to find out what is the best way to linearly combine these basis functions. Okay, and you want to minimize it. So the typical error function that we'll be using is the least squares is the square error function. Uh, so the error function typically is going to be this. So uh, E is typically uh, the square error function. Okay. If effectively what you are doing is you are computing the mean squared error, and uh, you want to compute these alpha ones to alpha r's, which minimize this mean square error, right? Okay, so let's see how this becomes a problem of the least squares problem, which we just solved before. So you will write so this f hat alpha 1 to alpha r. I will just for the sake of convenience, I'll write it as y hat. Okay. So each y hat uh, at some xi. So remember, this xi's are your training sets. So they're basically the points at which you know the exact value of x. So this I'm going to just write it as yi. This is just an approximate. This is just a notation, and so this is equal to uh, alpha one phi one of phi one of xi plus dot 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 up to alpha r phi r of Right. So, so now you want to minimize this. You uh, want to minimize yi minus y hat I, where yi is obviously the exact value of the function. So let me just write it. Yi is equal to f of xi. This is known to you, and you want to minimize this quantity, right? So this is equal to uh, well, well. So in a matrix notation, you will write it in this way. Um, so you want to minimize. So you write you form a matrix Y where Y is basically equal to uh, Y1 up to some Yn, and then you form another matrix Y cap, which is equal to Y cap 1 up to Y cap uh, n, and you want to minimize this. You want to minimize Y minus Y cap norms there. This is what you want to minimize. And so y minus y cap, well, if you just plug this in, uh, so what is y cap? Let me just write it down. This y cap is equal to a certain matrix, which I'm going to write it as 5 times this matrix. Okay, and what is this this capital 5? So this capital 5 uh, is a matrix where the entries are like this. So it's so this is the column corresponding to phi 1. This is the column corresponding to phi 2. Likewise, this is the column corresponding to phi I. So basically, phi ij is equal to phi j acting on xi. Okay. So essentially, I have taken these quantities and I've fit them into a nice matrix. Okay. So this matrix is known to you. This is a matrix of scalar quantities. So each of the entries is known to you because uh, the phi ones to phi r's are functions which you know beforehand. It's functions that you know, and you've evaluated these functions on each of these data points, x1 to x9. Okay. So you know them exactly. And so then what you are doing is you want to minimize with respect to alpha, you want to minimize y minus phi alpha. This is what you seek to minimize, and with respect to the two norms. And you know the solution. So this is going to be solved by alpha star um, is equal to phi pseudo inverse times y. Okay. Yeah, I hope it's clear. Uh,
Sir, if possible, can you give one example for functions and one example
yeah, I
for
mean,
matrices?
once yeah,
Just
once we look at
yeah,
the assignment problems, we're going to get examples there from there. Okay.
okay.
Um, just give me 1 second. Uh, Okay. So let's jump into the problems for week 7. Yeah, you wanted some examples, is it?
Yeah,
Uh,
just we
hmm.
are new to this area, I mean concepts.
Okay,
So
okay,
it would be good if you can explain
okay,
to
okay,
just
okay.
idea
Right.
through
So
one or two
let's take one
examples.
example of linear regression. So one example that we have is what if we try to uh, approximate a function using a polynomial? Okay. Uh, so uh, uh, approximating using polynomials. So let's say you fix. So if you have a polynomial, then the basis functions for the polynomial are the monomials, right? Uh, um, okay, just give me 1 second. A polynomial is not actually ideal for vector inputs. Um, hmm. Okay, okay, okay. So yeah, so let's take uh, yeah, I mean, you can still approximate using polynomials. It's just that it's going to be quite large. Okay, so let's first take an example where we actually want to approximate this using some polynomials. So let's say uh, we have a function f uh, which we want to approximate, which takes some Rm to R. Okay, and your training set is given to you. Let's say x1. Let's say x1 to xn is your training set. Okay, and I what I'm asking is, can you approximate this function f with a bilinear form? Okay, so I choose a bilinear form. So let's say, okay. So how does a bilinear form look like? Uh, okay. Um, okay. Yeah, okay. I'm actually trying to make up a problem from scratch. So just give me a minute. Um,
Yeah, no issues.
right. So, mm, hmm, hmm. Okay, okay. So let's say it is given to you that f satisfies this property, that f of Sx, where s is some scalar, is equal to s squared times f of x. Okay. Let's say this is given to you. So when this is given to you, you can basically say that f is a bilinear form. It's a bilinear function, which uh, yeah. So you can actually find a bilinear function where f x is equal to this bilinear form acting on x comma x, where sorry, I'm saying bilinear all the time. No, it's not bilinear. What I mean is quadratic form, where B is a quadratic form.
Yeah, that's what I'm thinking. Bilinear
Yeah, bilinear
modes
is the term.
terms are coming in complex analysis. So
Yes,
that's
yes. I
what.
mean, I'm thinking of quadratic,
So
but I'm
quadratic
saying
forms
bilinear.
is more convenient word, I guess. Yes.
Yes, that's right. Yeah. So, I want to approximate I know that f is a quadratic form, but I cannot tell exactly what is the quadratic form. So I'll try to come up with a quadratic form and say and try to say something about with respect to f. Okay. So the quadratic form that I come up with is something like this. Uh, there is some matrix A, uh, um, um, some A11 up to some ANN, and my function f hat, which is parameterized by A, is equal to x transpose AX. Okay, so you want to learn this A. I'm writing it as A. Let's write it as alpha because I've used alpha all the time. So let's write it as alpha. So alpha is this big matrix. So if you kind of break this thing down, you will see that this is basically equal to some summation of alpha ij x uh, xi times xj.
Is alpha is diagonal matrix or symmetric
No, no,
matrix?
alpha is not a diagonal matrix. It's some
Symmetric
matrix.
matrix.
Uh, yeah, it's a symmetric matrix. Alpha
Symmetric.
is a symmetric. It's a symmetric matrix. Okay. Alpha is a symmetric matrix. Yeah. So essentially, what is happening is that uh, this is my choice of basis function. So uh, uh, yeah. So how many basis functions are there? If it's a function from M, there are M squared basis functions that I have chosen. And I'm going to write this f hat alpha as equal to this sum over of alpha ij xi xj I comma j. Okay. Now you have your training set with you. So what you do is you form this matrix phi, okay, where uh, where uh, phi ij. Oh, okay. I can't use ij over here. Where phi I k, where k is, so there are m squared basis functions. Um, okay, let's assume that it's not a symmetric matrix. Okay, it will make our lives easier. I'll tell you why. Uh, a, a is a alpha is a matrix. Uh, it's not a symmetric matrix. Um, so each of these yeah, or you can also take it to be a symmetric matrix. But in that case, what happens is that you do not, there are not m squared, uh, there are no longer m squared basis functions, but m into m plus 1 by 2 basis functions, which is fine. That's not a problem. So this k runs from 1 to m squared. And phi I k is basically equal to uh, Um, yeah, so you take the right. So okay, so essentially, this is a matrix, and you have I and j. So you will write this k as equal to some. Uh, yeah, every k can be written as some mp plus q, right? Um, yeah. So this phi I k is equal to xi xi uh, xi p xi q. Yeah, so there are m squared many basis functions, but you have to linearize them. So the basis functions are represented like a matrix, But when you form this matrix phi, like here, so there are m squared many such uh, there are m squared many such basis functions. And because the m squared many such basis functions, what you have to do is, so at phi I comma k, you take the ith data point. So the ith data point, and in that ith data point, uh, based on this number k, you will decide which coordinates to pick. So if this k is represented as some mp plus q, which every k can be because k is between some 1 to m squared, uh, you will write this as equal to xp times xq. So this is how you will form this matrix phi, and the alpha, that's again this alpha star which we want to find out, is going to be this phi pseudo inverse times uh, f, where f is basically this matrix. It's a column vector, uh, x1 up to x, which is given to you. Okay. Um, hopefully you can see what I'm trying to say. You can take some small example where, let's say, uh, uh, like a handcrafted example where you take R2 to R, and so then any bilinear form you can kind of write it as a x1 squared plus b x2 squared plus c xy. Okay, and then you have three parameters to work with, a, b, c, and you take some function f. Uh, you come up with a with some data points, x1, x2. Sorry, you come up with some data points, x1, x2, x3, and you set some values to those guys. So you set y1 to be equal to fx1, y2 equals to fx2, y3 equals fx3, and so on. Uh, and then do something like this. So one exercise that I am giving you is as follows. So pick a uh, symmetric quadratic symmetric quadratic form, or basically pick a quadratic function. Pick a quadratic function of two variables. So you pick that function. So you basically know f, and uh, and then uh, pick some and then pick an approximator, which is basically some ax1 squared plus bx2 squared plus cxy. So you pick some approximator of this kind, of this quadratic form. So this quadratic function itself actually looks like uh, some a bar x1 squared plus b bar x2 squared uh, plus c bar xy. So it actually looks something like this. Okay, but what you do is, so now you try to see that how many data points do you need uh, uh, approximate this as closely as you want. Okay, um, right. So that is an exercise. So if you pick like 3 points, then you're going to get some estimate of A, B, C. But if you pick many points, you're going to get a better estimate of these A bar, B. So A bar, B bar, C bar has to be estimated by these A, B, C, and you can check how good an estimation you can get by increasing the number of samples. Okay. In particular, this is an area of So when you do these kinds of parametric estimations, uh, uh, one often asks the question that if I take a sample size large enough, so if my test set is very large enough, then will uh, uh, then will my estimator actually converge to the actual value? Okay, and based on that, you have biased and unbiased estimators. So, not going into that right now. Maybe in the following weeks we'll have questions like this. But this is something. This is an exercise that you can do. This is not an exercise by hand, by no means. You have to program this exercise. Okay. All right. Hopefully it's clear. Um if there are no further questions, let's look at the problems of this week. We don't have a lot of time, so we may look at a few problems and then look at the other problems the next. Okay. Um, all right. Yeah. So all of these exercises here are programming exercises. So yeah. So hopefully you're familiar with Python programming. So you will need to learn Python programming in case you're not familiar with this. Uh, but
Is it
what I will do,
necessary that for doing
yeah,
this,
yeah,
uh, know the
yeah,
Python for doing these programs?
uh, yeah, you'll have to know Python for doing these assignment problems because
What about those who are those who are not familiar with Python
so you
and
have to know
Python?
Python. Otherwise, these assignment problems you won't be able to do them because they're not problems which you can solve by hand. They're not meant to be
Okay,
solved by hand. They're meant to be programmed actually. Okay.
okay, that's it.
Uh, if you don't know Python, then you have to know something equivalent. Uh,
Okay, okay,
something that does linear algebra manipulation. So, in case you don't know Python, then if you're familiar with C, C++, there is LAPACK, which is a linear algebra package. Because everywhere you will be using linear algebra here only. So, LAPACK is lets you do linear algebra in C or C++, but
mhm.
it's way less convenient. Like Python would be the most convenient. Or if you know things like Julia or other programming languages, that's also fine. But I would suggest to use Python and NumPy, SciPy, all those.
Okay.
Yeah. Yeah. So what I'll do is that I'll give like a general outline of what the problem is requiring you to say, like basically what is being asked of you. I cannot program and compute the answer. I will just uh, I will just give an outline of what is required to do in the problems, and the coding would have to be done. So if you look at the lecture notes for this week, you will see that in the lecture material, there are code snippets that have been provided. So you do not have to write a whole lot of code. You just have to use those code snippets and modify them for your uh, for the problem. Uh, okay, so the first is basically this. Um, hmm. So in this first problem, you have to generate P and Q. Okay. So these are basically random vectors, and each pi is uh, is uniformly generated from this range. Same for qi. So basically, uh, pi comma qi. Uh, these are sampled from the uniform random distribution. Uh, Now, you generate a function of these two random variables. So b is a function of these two random vectors, basically. Uh, uh, okay, which is defined in this way. So b uh, actually is not this. It's actually plus one comma minus one whole to the power 100. So bi is equal to one if piq is greater than one, if is greater than zero. So this is how you define the function. So essentially, what you have to do is you first generate these two random vectors, then you compute this bi. Okay. Once you've computed this bi, right? So once you have computed this bi, uh, okay, okay. Hmm. Yes. Okay. Right. So this is a classic example of least squares approximation. So what you have to do is, I hope it's clear what they are requiring you to do. So these are your, if I have to map it to the least squares problem that we were dealing with before, so what is this P and Q? So uh, right. So the variable that you are studying, so the function that you are studying is B. Uh, B is the uh, function being studied. Okay. Uh, and how is what is B basically? So B looks like this. So B is a function. B is a function from R2 to minus one comma plus one, which looks like this. So this is not required strictly, like you can mechanically follow the steps and get it, but I'm still drawing a picture so that it's clear what B looks like. So if you look at the region, so this is the P axis and this is the Q axis. So if you look at the region PQ is greater than 1, uh, which is going to be this hyperbolic region. So you look at this hyperbola, and yeah. So if you look at this region, and if you look at this region, uh, uh, then in this region, B is going to assign 1. And for this region, it's going to assign -1. So this region gets -1 and this region gets +1. Okay. So this is the function that is being, that is the function you have to approximate. Now notice that this function is it's a very, it's not even a continuous function. Like, first of all is that it's not even a continuous function. It is a piecewise continuous function. So it is -1 over this region and +1 over there. So it's a piecewise continuous function. But you are still asked to approximate this piecewise continuous function using the following basis functions. So the basis functions that you're going to use are as follows: one, p, q, p squared, q squared, pq. So this is my choice of basis functions. All right, and so now essentially what you do is that you use b to and the data set that you're going to use, sorry, the training set that you're going to use is this random vector. So the uh, training set has 100 vectors. Okay, um, and the 100 vectors are basically this: uh, p1, q1, p2, q2, up to p100, q100. So this is the training set where each uh, pi and each qi is drawn uniformly from -10, 10. Okay. Uh, Now, based on whatever pi and qi you get, you're going to get b1 up to b100. Uh, you can form the training. You can form this matrix phi as uh, uh, so phi is basically a 100 × 6 matrix, right? Uh, where the six correspond to these basis functions: uh, 1, p, q, p squared, q squared, pq, and 100 rows corresponding to the value at each. So the first column will be equal to 1. Uh, the second column would be equal to the p value, which is uh, uh, p1 up to p100. The second would be q1 up to q100. The third would be p100 times q100 and so on. And finally, you are going to minimize uh, b. So if I write this b as a vector, which is b1 up to b100, you're going to basically compute. Uh, you're asked to minimize this thing. You're asked to minimize b minus uh, pi times alpha, where alpha is, so you will combine this using these parameters alpha. So you're going to write a function b hat, where b hat is equal to alpha 1 times 1 plus alpha 2 times p plus alpha 3 times q plus alpha 4 p square plus alpha 5 q square plus alpha 6 pq. Okay, so if alpha is alpha 1 up to alpha 6 transpose, uh, you are asked to minimize this. So this is what you are asked to minimize, and you will get some alpha star, and then they're asking you which basis function corresponds to the largest value in x. So you will look at alpha, whichever alpha I is largest among all these alpha i's, you have to report the fi corresponding to that. Okay. When doing an experiment like this, make sure that you're, because uh, the vectors are drawn uniformly randomly, make sure you repeat this programming exercise at least 3 times so that you get like uh, uh, so that the chances of getting a wrong answer because of some randomization issues do not occur. So run them at least 3 times. Okay. Hope it's clear what you are asked to do. Okay. So I explained this first problem in a uh, uh, in uh, in a lot of detail, so that it's clear what you expect it to do. The following problems I'll give brief outlines. Okay, hopefully it's clear. Let's move on to the second problem. So in the second exercise, you are supposed to download this MNIST dataset. The MNIST dataset is widely available everywhere. It is uh, it is a dataset consisting of handwritten digits. Okay, and the idea is to basically classify the digits. Uh, you may want to look at the lecture notes. In the lecture notes, there are code snippets given already. So you may use the code snippets to already download the MNIST dataset. So there step-by-step instructions are given how to download the MNIST dataset, how to crop the image by 5 pixels from both rows and columns, how to vectorize. So all that information is given to you. Uh, or rather, how the code snippets are actually given to you. You just have to copy paste them. Uh, Hmm. Right. So in this second problem, you are it's a linear regression problem. I hope it's clear what the problem requires you to do. So just giving like a brief outline of what this is, in case you're not familiar with these kinds of data set manipulations. So it's a data set of images. Okay, so each image is going to look like something like it's going to be. What is an image? So an image is represented as pixels. So it could be 64 cross 64 pixels. It could be 32 cross 32 pixels. It could be 256 cross 256 pixels. It is some number of pixels. Now, what is a pixel? So think of it in this way. Let's say you're looking at the number uh, 5. Okay, 5. Right. Now, the pixel is like it is. Think of a box like think of this bounding box, and think of some rows and columns. Okay. So if it's a 256 cross 256 image, it's going to have 256 rows and 256 columns. Okay. Now, each cell contains a number. So each ij contains a number. Okay. Uh, now, if uh, if let's look at 5. Okay. Now, if the cell is empty, that is, if there's no, that is, if there's nothing written over here, then the number is going to be small. And if the cell is, if the cell has something written on it, let's say 5 passes through this cell, then the number contained in this cell will be a large number. So effectively, in this way, the cells which have a part of that number will have a larger number, and the cells which are empty will have a small number. Okay. So now, so effectively, what this means is that given an image I, you can vectorize it. So you can think of it as a 256 cross 256 size vector. So each image I belongs to R 256 cross 256. Okay, and what you are asked to do, you are going to have a linear regression model. So your job over here, the goal of this MNIST dataset is to basically classify classify the different numbers, is to distinguish one number from the other, and to basically classify the numbers. So in this case, you are asked 9 classification problems. The classification problems are as follows: 1 versus 0 up to 1 versus 9. Okay. So for each of these classification problems, you have to fit a linear regression model. So the linear regression model is basically this. Um so in a linear regression model, if x is a vector that is drawn from Rn, then the approximator function y hat is equal to a1x1 up to amxn. In this case, m is equal to 256 cross 256, or whatever is the size of the images in the MNIST dataset. You can check that out. Now, okay. So now, what happens is that for each image I, uh, right, for each image I, you have a label. Okay. So let's write a function y on each image I. So let's take the first problem. So the first problem is 1 versus 0. So you have a function on each image I where this function is equal to +1 if if uh, if if the image is uh, 1, and -1 if the image is 0. So the image is 0, you take it as 1. Uh, if it's 0, you take it as -1. Okay. Um, and now you take your linear regression model, and in that linear regression model, what you do is that uh, uh, yeah. So in that linear regression model, if right, so if this y cap for any image I is greater than 0, you set it +1. And if this y cap I for any image is less than or equal to 0, you set it as -1. Okay, right. And now, yeah, and now you have to compute a set of A1s to AMs such that the uh, total classification error is minimized. Okay, so um, you want to do this. Uh, you want to do yi minus y hat of I squared. So this y hat in turn depends on a1 to an. So I'm going to write a over here squared. You want to minimize the sum of this, where I is an image that belongs to this data set. So for all images in the data set, you want to solve this minimization program. Minimization of a this. Okay. Um, yeah. So this is the program that you have to solve. Um,
Amrit, are you there?
yeah, I'm there. I'm there.
Okay.
Yeah, even I'm not able to quite understand the last statement of this question. Uh, when using the ground truth provided in the test set, find out which of the nine remaining classes is most similar to class one. Uh,
Actually,
Even
this
if the
is
class,
completely new to me.
yeah,
This concept
mm,
is completely new to me. Even yeah, I haven't watched the lectures also.
okay, okay, yeah, maybe you can have a look at the lectures.
Yeah. Okay.
Uh,
Okay, Amrit. Then we can end this session. Maybe we will try to solve
yeah,
the by looking at the lectures. The problems we'll try
yes,
to solve problems by
yes,
looking.
yes, yeah, yeah,
And then
yeah.
next week we will
We'll
discuss.
look at the, we'll look at, so we have looked at the theoretical ideas more or less. So
Okay.
next week, what I'll do is I will not go into the theory part because we'll have to look at the problems, the remaining problems from this week, as well as the problems from week 8.
No,
So I'll
actually, if possible, maybe you know you better to ignore this this week problem, last week problems. Just
uh,
focus on the week 8 problems.
okay, that's
Content.
also fine. That's also
Yeah.
possible. Yeah, I can also do that. But we'll see. We'll see. This week there aren't many people who joined. Maybe next week there will be other people, so they may have some questions. So we'll see what happens next week.
Yeah. No
Uh,
problem. It's completely based on the audience, participant only.
yeah.
If they
All
request
right.
to solve some problems in the previous this week problems, we can solve some problems.